This meeting is being recorded.
My name is Nupuri, and today I will be talking about my Raspberry Pi project for CNIT 176. So, before I get into my project, I would briefly like to overview the table of contents. I first will start off with a basic introduction about myself, then lead into the business case, followed by the system architecture and the setup and tools for used for the project. I then will take a deep dive into the nitty-gritty details of my project and end with a live demo and conclusion for the project. So, hello, my name is Nupuri, and I'm a freshman studying computer information technology here at Purdue University, and I'm passionate about all things cybersecurity. Now, I have a keen interest in cloud security and want to work at AWS as a cloud security engineer in the near future. So, the business case 40%. I'm going to let that sink in because that's how many attacks begin with reconnaissance, silent scans that go completely unnoticed. Now, most networks, especially at home, on campus, or in small offices, have no visibility into this stage. According to IBM's X-Force Threat Intelligence Index, nearly 4 in 10 attacks start this way, long before malware or exploits are even used. And that's the gap that I wanted to discuss and to address. Detecting the very first step of an attack when it's easiest to catch and act on. So, what's the solution? My solution is a lightweight real-time intrusion detection system using a Raspberry Pi, Python, and the Scapy library. And with my project, I focus on two patterns that signal reconnaissance: ICMP echo requests or pings, and TCP SYN packets used in stealth port scans. If either is detected, the system logs the alert and prints it instantly. It runs completely offline, is easy to deploy at the edge of a network, and is especially suited for environments that don't have enterprise-grade tools. So let me show you how this works in context. Think of of my IDS as a motion detector at your network's front door. The Raspberry Pi, or the IDS, sits at the edge before any firewall or endpoint sees the traffic, and it monitors all inbound packets. So now when an attacker sends pings or port scans, the Pi sees them first and logs them immediately. This is critical for low budget setups because you don't need to stop the attacker, you just need to see them early. Now let's look at how the Pi actually processes these packets internally. So, taking a look at the system architecture for this project, we see that the packets arrive through the WLAN interface and are captured using an AF packet socket, which is a raw Linux socket that gives access to the Ethernet frames. From there, two paths begin. The first is ICMP echo requests, which is the yellow path here. The script logs the ping source in the destination, and then it writes the alert to a file and streams it to the terminal. Similarly, for TCP SYN packets, we're going to capture the flag, ports, and IPs, and then also write and print the alert as well. All alerts go to this alerts.log file, which we'll see later on, and are streamed using a tail command. The entire detection flow is offline in real time. Everything happens locally and instantly. So let's go on to the setup workflow, which is essentially building the IDS. Now, first challenge for me was getting the Pi to even see the traffic. Because Purdue Wi-Fi blocks peer-to-peer traffic, I had to use Tailscale, a mesh VPN to tunnel traffic from my laptop to the Pi using a virtual interface called Tailscale 0. To verify the Pi was actually seeing the packets, I used the following command. This confirmed that both ICMP and TCP SYN traffic was arriving. Once that was working, I ran pings and Nmap scans from my laptop and launched the IDS script to start detecting in real time, which we will see in a moment. So, with the IDS script, the script uses Scapy's sniff function to capture packets from the Tailscale interface and sends each one to detect packet, which is a detection function. Now, if the packet is an ICMP echo request, it's going to log it as an alert. And if it's a TCP SYN packet, it's going to extract the ports and log it as a scan attempt. Each alert is written to idsalerts.log and is flushed immediately, so you can view it live in a second terminal using tailf. It's clean, simple script, but it's highly effective. So let's take a look at a live demo of the So now that we saw the demo, I just want to quickly break down what exactly happened. So I had an attacker machine, which was just my Windows laptop. And from there, I ran two tests. First, I used the ping command to send 3 ICMP echo requests directly to the Raspberry Pi. That simulated a basic probe to see if the Pi was even online. Then I used Nmap with the PN and SSS flags to launch a stealth TCP SYN scan targeting ports 22, 80, and 443, the ones typically used for SSH, HTTP, and HTTPS. Now for the Raspberry Pi. I had two terminals open. In one, I was running the detection script. That's where the real-time alerts get printed immediately when the packet matches the rules. And the other terminal, which wasn't shown in the video, but was also running, was the tail command. Now this command shows the log file and updates live as the system writes to it. And so as soon as the Pi received the ping packets, we see this alert. We see the alert ping detected from the IP. And then right after launching the Nmap scans, we see the new SYN packet alerts. And the similar entries are for ports 80 and 443. So from a first glance, and looking from both terminals, that is, I could see what kind of scan happened, which IP it came from, which ports were targeted, and exactly when it occurred, thanks to the logging feature. Now, this live feedback confirmed the IDS was working, capturing real attack traffic, parsing it, and reporting it with full context. No delays, no missed packets, just real-time visibility from the edge. So let's connect this back to what we learned in class in CNIT 176. Now, in class, we learned about how packets, we learned about input and output. And so in my project, packets arrive through the wireless adapter, a peripheral device that we classify under the I/O and systems architecture. From there, they're passed into an AF packet socket, which is the memory mapped I/O, giving user space access to raw bytes. In my IDS script, Scapy's sniff function acts as interrupt-driven I/O, as it waits for incoming packets and responds when triggered, not through polling. The alerts are then written using file descriptors and system calls, which ties into how programs interact with the OS and kernel-managed resources. And all of this is running on the Raspberry Pi's ARM instruction set architecture, where Python is eventually broken down into machine instructions using the fetch, decode, and execute cycle that we discussed in class. And lastly, building something that touches so many layers of the system wasn't without many challenges, and I ran into plenty of them when developing and testing the setup. So let's get into it. There were plenty of gotchas. The first one was Scapy needs root access to sniff packets. If I forgot sudo, it silently failed with no errors. Just a quick Linux fact. I also had an import state error with the sniff command, and that was fixed by switching to from scapy.all import, installing all the necessary packages and dependencies. Now, my script initially threw a file not found error because the log file didn't exist yet, and I had to manually create IDS alerts.log and give it the right permissions. I also ran into an error when I was testing the AP mode with hostapay. The service kept crashing, and so I found out that the hostapd config was missing, and the correct Linux driver NL80211 was added. After adding it, the AP worked perfectly. Lastly, I wanted to go above and beyond with this project by sending alerts to AWS CloudWatch. And so when trying to do this, I hit an incomplete signature exception. Turns out my IAM credentials was malformed, and so I fixed that too, but chose to keep the system offline for stability. So what are some lessons that I learned? Well, this project helped me grow far beyond code. I learned how to validate packet level traffic, troubleshoot Linux networking, and interpret protocol behavior using Tshark and Scapy. I saw how instruction sets, system calls, and memory access happen behind the scenes in a working system that I built myself. Even though AWS CloudWatch isn't active here, I now know how to integrate cloud-based logging, define IAM roles, and send alerts remotely. It taught me that working systems are always layered, and that understanding those layers is the key to building secure, reliable tools. Now, going forward, I want to change the system in a few ways. The first way is to create a systemd service to run the IDS on boot, so without the sudo command, so I don't have to start it manually. I then want to expand the detection, maybe add UDP packets, monitor full TCP handshakes, and eventually look at HTTP payloads as well. I then want to rotate the logs and restrict access permissions for better security. And lastly, I would like to scale the project, deploying multiple Pi sensors and centralizing logs to a single dashboard. This will be coupled with AWS CloudWatch with an integration like a SYN, such as Elasticsearch, giving me full visibility and learning from anywhere. Overall, what started as a local Python script has become a foundation for something much bigger. And I'm very excited for what you guys will do in the future. And I hope I have inspired you to create your own Raspberry Pi projects. Thank you again for listening. Thank you.